Good day. We're going to talk about the weight. Now, recall Newton's second law. Newton's second law of motion states that the sum of all the forces acting on an object is equal to the mass of that object times the acceleration of that object. So consider an object near the Earth's surface. This object has a mass, m, and we actually refer to that mass as the inertial mass of the object. The inertial mass is the object's tendency to resist changes in its state of motion, its sluggishness. If the mass is bigger, then a bigger force is required to achieve a certain rate of acceleration. Now this object is near the Earth's surface. And if we consider this object to be free falling near the Earth's surface, then that means that there's only one force acting on that object, and that force is the force of gravity. So this force of gravity actually causes this object to accelerate downwards. And experiments have shown that that acceleration turns out to be 9.8 meters per second squared. And it doesn't matter what mass the object has, and in this case, since the mass is bigger, the gravitational force is also bigger, but as it turns out, they have the same acceleration, 9.8 meters per second squared. So that means if you have two objects, a lesser heavier object compared with a heavier object, and if you drop them from the same height, they will reach the ground at the same time. I have a challenge for my students. I will give you 5 bonus quiz points if you send a video of yourself to my email holding a rock or something heavy in one hand and a crumpled piece of paper on the other, and you drop them from the same height and show that both objects hit the ground at the same time. If you elicit a good reaction to seeing that they hit the ground at the same time, then you have bonus points. Okay, so this is fascinating, right? Two objects, completely different masses, they have the same gravitational acceleration, 9.8. And since this value is so special, they gave it a symbol of g. Eventually, the scientists realized that this g is only true for the Earth. The g, or the gravitational acceleration on the moon, is 9.8. It's not 9.8, but 1.7. I think 1.7 meters per second squared. Nevertheless, this gravitational force that is exerted on objects near the Earth's surface is known as the weight. And so the formula of Newton's second law reduces to weight is equal to m times g, where g is 9.8 on the Earth's surface and another value somewhere else. So W is the gravitational force acting on objects near a celestial body. Mass is the inertial mass, m is the inertial mass. It is the measure of the sluggishness of an object, tendency to resist changes in motion. And g is the acceleration of the object due to the gravitational force that the nearby celestial body acts on it. These are values for the g. for various celestial bodies. Now, this is a very wonderful uh, generalized definition for weight. The weight of a body is the total gravitational force exerted on the body by all other bodies in the universe. Like what? That's a very clever definition. Why? Because let's consider you. If you are on Earth, the definition says that your weight is the total gravitational force exerted on you by all other bodies in the universe. So it's not just the gravitational force that the Earth exerts on you, but it's also the gravitational force that the other planets exert on you, the sun, the stars, the black hole in the center of the galaxy. All of these heavenly bodies are contributing to your weight. But the thing is, the only contribution that matters is that of the Earth's, because all of these other objects are far away and their contribution is little to zero. And what makes this definition clever is you can still use that definition even if you go to somewhere else, like the moon perhaps. If you fly a spaceship and go to the moon, then your weight is still the total gravitational force by all other bodies. So the sun still contributes to your weight, the planets. The earth still contributes to your weight, but now the earth is far away. So the only real contribution is when you are on the moon, the gravitational force that the moon acts on you. So I really like that definition. As I mentioned earlier, here we have a medicine ball, clearly much heavier than the basketball. They will hit the ground at the same time if they are released at rest from the same height because they have the same acceleration. And true enough, I know it's a simulation, but true enough, that's what we see. Notice it even has a little bounce near the end. So what happens here? Why do they fall to the ground at the same time? Well, the medicine ball definitely has larger weight, and the basketball has a lesser weight. But the medicine ball experiences a greater gravitational force because it has a bigger mass, but it also has more mass, which means it has more inertia. Let me elaborate further. As it turns out, the basketball has smaller mass and it also has smaller weight acting on it. So actually the ratio works out to be 9.8 meters per second squared. Now the medicine ball has a bigger mass, but it also has a bigger weight. So even if the gravitational force acting on this medicine ball is huge, it doesn't accelerate faster because it also has a bigger mass, or it's a bigger inertia. And the ratio still works out to be 9.8 meters per second squared. Just to add a few numbers. Even if the heavier mass experiences a larger gravitational force, it also has a lot of inertia, so it requires greater force to accelerate it at the same rate as a lighter object. Ultimately, all objects, regardless of mass, will have a gravitational acceleration of 9.8 meters per second squared near the Earth's surface. I want to emphasize the word near the Earth's surface because when you're above significantly higher above the Earth's surface, then the number 9.8 is no longer applicable. I'm just gonna give one example. Suppose this basketball has a mass of 1 kilogram. You will find through calculations or experimentations that the ball will have a force of 9.8, will have a weight of 9.8 newtons. So that works out to be 9.8 newtons per kilogram. And if you know what newton is equivalent to in terms of fundamental units, you will find that newtons per kilogram is equivalent to meters per second squared. Let's say the medicine ball is 5 kilograms in mass, but you will find that, I hope my math is correct, the earth will pull on it with 49 newtons. So when you divide, you will get 9.8 newtons per kilogram or meters per second squared. So our previous lesson, we talked about law of universal gravitation. And if you model the Earth as a spherically symmetric body, and it acting on an object on its surface is another body, which you can approximate to be like a point object, since it's so much smaller compared to the Earth. Here in the drawing, the mass is significantly smaller. So you can use the law of universal gravitation, gm1 m2 over r squared, to calculate the force between them. And there you have it. me is the mass of one of the objects, which is the Earth. M is the mass of the other object. And RE is actually the radius of the Earth, but that approximates to be the center to center distance between the two objects. Since one of the objects is so much smaller, essentially the gap between the Earth and that object sitting on the Earth is just the radius of the Earth. You know weight is just Fg, so we substitute Fg to be weight. W is equal to gm em over r squared. And our formula for weight is mg. And now, m here, it refers to the mass of the object on the Earth. And it appears on both sides of the equations, so we cancel that out. We now have a formula for the acceleration due to gravity at the Earth's surface. Capital G, which is the gravitational constant, m, mass of the Earth, r is the radius of the Earth. So, this is for the Earth, but a general formula would be G is equal to G m over r squared. So this is not only for the Earth, but for any other celestial body. Where m here is the mass of that celestial body. Now there might be some confusion because here m is the mass of the object on the celestial body. So I suggest that you put the subscript s, which means source, which means it is the source of the gravitational force acting on the object on the surface. G is also known as the gravitational field strength. It is independent of the mass of the body. And here, in this formula, this is for the gravitational field strength of the Earth. Let's just check if we get 9.8 when we substitute the known values for the mass of the Earth and the radius of the Earth. And if you use your calculator, you can actually get 9.8 meters per second squared. Here's one example. An astronaut weighs 700 newtons on Earth. As it goes further and further away from the Earth's surface, what happens to the gravitational force of attraction it experiences? Here's what I'd do. I'd ask you to do this on your own. I think you have enough knowledge to know how to solve this problem. You will find, though, that the answer to this first question, what happens to the gravitational force of attraction it experiences? Well, we have this formula, capital G m over r squared. Find that G is inversely proportional to whatever r is. R is the distance from the center of the source to wherever we want to find gravitational field strength. So the farther the astronaut is away from the center, the weaker the gravitational field strength. And in fact, the factor is inversely proportional to the square. So I want you to solve this problem in your notes, and I will collect that solution later. This is another problem, and I have the answer at the bottom. That's 3.7 not 3.7. So thank you very much.